D'Alembert's principle states that algebraic sum of the forces acting on a body along a given direction is equal to the product of mass and acceleration in that direction. That is, net force is equal to mass into acceleration. We can write acceleration in various ways. First of all, by the definition of acceleration, we know that it is change in velocity by time. So for instantaneous acceleration, we can say it is dv by dt, where v is velocity of object. This can also be written as dv by dx multiplied by dx by dt, where x is displacement of the object. This is equal to dv by dx multiplied by v, as dx by dt, that is change in displacement by change in time, is nothing but velocity itself. Hence the third way to write acceleration is double derivative of displacement by time. Now let us solve a question. The question is as shown. If you wish, you can give it an initial try, but if you get stuck, don't worry, it's just the first question. Now let us solve this. We have a body of mass m falling from rest, and it is opposed by an air resistance that is kv square. The body passes through a distance x to attain a velocity v. We know that the net force is equal to mass into acceleration. Hence, mg minus kv square is equal to mass into acceleration, that is v dv by dx. It is given that mg is equal to ka square. So let's substitute that value. Hence, ka square minus kv square is equal to mv dv by dx. Now taking terms of v with dv and remaining terms with dx, we get v by a square minus v square dv is equal to k by m dx. Now integrate both sides, we get minus 1 by 2 log a square minus v square is equal to k by m multiplied by x plus c. We also know that the body is initially at rest, that is x is equal to 0 and v is equal to 0. Putting these values, we get minus half log a square is equal to c. Now let us use the value of c that we just found. We get half log a square minus v square is equal to kx by m minus half log a square. Simplifying further and using property of log, we get 2kx by m is equal to log of a square by a square minus v square. And that is what we were required to prove. Remember that the format for solving such type of problems is going to be the same. Now let us move to the next topic, that is application of differential equations of first order. The first application is of simple electric circuits. To understand, some basic relations are to be known, like I equal to dq by dt, or that q is equal to integration of I dt. Voltage drop across resistance R is equal to Ri. Voltage drop across inductance L is equal to L di by dt. And voltage drop across capacitance C is equal to Q by C. Problems on this topic are solved using Kirchhoff's laws. The first law is that algebraic sum of voltage drops around any closed circuit is equal to the resultant EMF in the circuit. The second law is algebraic sum of the currents flowing or from any node is 0. The circuit that we are going to study in this video is resistance and inductance circuit. Here, using the first Kirchhoff's law, we add the sum of voltage drops, that is Ri on the resistance plus L di by dt on the inductor equal to E. This can be rearranged as di by dt plus R by L into I is equal to E by L, which is differential linear equation in I. If you don't know how to solve for general solution of this equation, click the I icon on the top right side of the screen. Moving ahead, comparing this equation with standard equation, we find that P is equal to R by L and Q equal to E by L. Integrating factor is equal to e raised to integration of p dt, that is equal to e raised to r by L multiplied by t. Hence, general solution is equal to I into integrating factor equal to integration of q into integrating factor dt plus c, which can be solved to get I into e raised to r by L multiplied by t equal to e by r into e raised to rt by L plus c. Now to find c, we put the initial condition, that is when t equal to 0, I is also equal to 0. Hence c equals to minus e by r. Hence our general solution becomes I is equal to E by R in bracket 1 minus e raised to minus RT by L. As t tends to infinity, we get maximum current. Hence Imax is equal to E by R. Now there are a few formulas which you can see. These can be easily ignored, but sure enough they might trouble you in few questions. So even though I don't recommend learning these formulas, you can refer these while solving practice questions and you are good to go. You can watch next video to see the next application of differential equations of first order, that is heat flow, or check the previous part of this chapter to understand Bernoulli's equations.